Okay. So, okay, so I think that last time we were we derived actually what is called the law of mass action. So what we are dealing with is a sort of reaction, chemical reaction, nuclear reaction, or in any case, any phenomenon related to particle interaction in which you can change the nature of the particles themselves. Could be a chemical reaction, but in any case, it could be also a particle physics process. And we said that by introducing the concentrations of the particles in the initial state and in the final state, so suppose that we have a reaction in which a particle or a molecule A plus B goes into another, for instance, couple of particles C and D, but this, can have also more states in the final state, more particles. This is rather general. Anyway, what we said is that if you take the product over J of Cj, where Cj is the concentration of particle J, and this is to the power of nu J, where nu J is the stoichiometric coefficient, then this is equal to the pressure, which is the total pressure of the system, to the power of minus J of sum of nu J, and then we have A of T. Okay, where A of T is a certain function of temperature, which is given by this formula, e to the minus 1 kb T sum over J chi J nu J, where the chi J are called chemical constants and characterize the chemical species of the ore or the particles they are taking part to this reaction. Okay, so this is the law of mass action. Of course, this law was derived in thermodynamical equilibrium, which in this case basically means chemical equilibrium, and was obtained by considering the fact when you are working at fixed temperature and pressure, what you have to minimize is the Gibbs free energy, the total Gibbs free energy. Therefore, if you have a change of number of particles, you should impose the sum of mu j dnj is equal to 0 at equilibrium, at a chemical equilibrium. Okay, and we said also last time that the way you can use this formula is to basically infer in which direction a reaction is going, in the sense that here, of course, we could start with a certain initial concentration of A and B, and we ask ourselves, and the initial concentration of C and D, for instance, and we ask ourselves in which direction the reaction will proceed, in this way or in this way. And in general, we don't know this, but by introducing the law of mass action, we can infer which direction the process will proceed, basically by computing this quantity here. This quantity here depends on the total pressure of the system, which is fixed, the total the temperature, the stoichiometric coefficients, and the nature, chi j, of the chemical species. Okay, so once you compute this term here, the right-hand side, then you can compute with your initial concentration the left-hand side and compare themselves. So, for instance, if you have, I think we have done a couple of examples. I just remind you the last one that we did. Suppose you have hydrogen going into molecular hydrogen. And the law of mass action in this case was the CH squared divided by CH2. This is the initial the concentration of hydrogen, so atomic hydrogen, whereas this is the concentration of molecular hydrogen, and this is equal to A of T divided by the pressure. Okay, so in this case, the law of mass action is the following, because nu1 is equal to 1, nu2 is equal to 1, and nu3 is equal to minus 1. Okay, so this is 1, 1, and minus 1. So we said last time, for instance, that if the pressure is small, then this term is large, and therefore is large also the ratio between atomic and molecular hydrogen. So that's, you know, it's a result that's rather intuitive. Small pressure, it's easier to have atomic hydrogen with respect to molecular hydrogen, whereas the opposite holds true in the case in which the pressure is large. If the pressure is large, it's easier to get molecular hydrogen. Okay. Now, what we will do now is to use the law of mass action to study a process which is the thermal ionization of atoms. And this is a rather interesting application of the law of mass action that, I remind you, was derived by basically was the starting point was to find the chemical potential in the microcanonical ensemble. So you can regard this example as a sort of application of the microcanonical ensemble, since for the first time, I guess the first time, you see which is the expression of the chemical potential in statistical physics. Okay. Now, the thermal ionization of atoms is a very important process because it has many possible applications, not only the quantity of ions that are in this room, for instance, but it's a very important process, for instance, also in cosmology, or in general in all the situation in which you have plasma, so that you have a mixture of ions and electrons. Okay, so this could be, for instance, typically the situation in stars, or it could be also the situation in the early universe, in which you have a separation between atoms and or ions and electrons. Okay, so it's a very important process, and we can study this process by using the law of mass action. So what we have in this case is the following. Suppose that you have an atom of species A, and let's indicate with A plus, so 1 time ionized, plus electrons, and this could go back and forward, forming a neutral atom. Okay, so this is the ion A plus, this is electrons, and this is the neutral atom. And now let's indicate with nu1 is equal to 1, the stoichiometric coefficient, nu2 is equal to 1, and nu3 is equal to minus 1. Remember that the stoichiometric coefficients are derived by writing basically this as this reaction as a sort of equation in which you have A plus plus E minus minus E0 is equal to 0. And for this case, you read the coefficients which are in front of the chemical species letters, and this is 1, no, 1, this 1, and this minus 1. Okay. Now, let's indicate, let me change page first. Maybe it's better if I do this. Let's indicate with C plus the concentration of A plus. And similarly, C minus is the concentration of electrons, and C0 will be the concentration of A0 of neutral atoms. Now, by writing the law of mass action, we get, by reading also the stoichiometric coefficients, that the product of C plus and C minus divided by C0 must be equal to 1 over the pressure, which is the total pressure, times A of T, where A of T was, I remind you, the formula of this quantity was exponential of 1 divided by kBt with a minus. And here we have the sum over J of nu J chi J. Okay? So what we need to compute A of T is the three chemical constant, which are K plus, chi plus, chi minus, and chi zero, to be determined. Okay? Now, of course, what we will do is to use the chi of T of the last time for monatomic and ideal particles. We can use the chi of T that we derived last time. Chi of T was equal to kBt logarithm of lambda cubed divided by kBt. Which can be written also in terms of temperature, so to make it more explicit, the temperature dependence. So lambda is the thermal de Broglie wavelength, which is provided by this formula, is h divided by the square root of 2 pi m kBt in general. Therefore, for a monatomic ideal gas of particles, the chi of T is this function kBt logarithm of, let me see here, we have a h squared, sorry, h cubed, then we have a 2 pi m to the power of 3 half, and then we have kBt, so 1 divided by kBt to the power of, so it's 3 half plus 1, which is 5 half. Okay, so this is the case of the chi of T, so the chemical constant for a monatomic and ideal gas of particles. And of course, as you see, it depends on the temperature and it depends on the mass of the particle itself. Okay, of course, there are now this 5 half, this 3 half, they depends on the type of molecules you are dealing with. So here in this simple case, we are considering the case of monatomic ideal gas. Okay, but this could be, this formula can be generalized to the case of molecules, for instance. Okay, one thing that we have to do in order to complete the calculation, well, to start with the calculations, is to introduce two modifications of this formula. First one, introduce degeneracy. And let's call G the degeneracy. What is this degeneracy? For instance, it could be due to the spin. Okay, instead of well, here we are not considering, we're considering spin equals 0 particles, but it could be spin 1/2 or 3/2 or 1, etc. Okay, so the first thing we will do is to introduce the degeneracy, and in the case in which you have degeneracy, one can show that the chi of t is modified as follows. So by introducing the degeneracy G, basically we have to introduce this factor G here in the denominator of the log of the chemical constants. We will prove this later, or we will justify the fact that we have the G, the degeneracy in the denominator of the chemical constant will be justified later. Actually, it's a calculation that one can do easily when introducing the grand canonical ensemble. So we will justify for the moment, but then we will derive it also in other ways. So this is the first modification that we need to do in order to proceed with the calculation. But there is another one that we have to do, and is to consider the fact that atoms, both ionized atoms and neutral atoms, have of course they have an internal structure. They have a full spectrum of energy in which they can occupy, and therefore we will introduce the ground state energy E0. Suppose that E0, and let me see how I call it, E0, 0, and E0 plus. Suppose that these two quantities are the ground state energy of neutral atoms and of ionized atoms. So it's ground.
Prof, mi scusi.
I have to change page. Yes, that was the point, right?
Sì, esatto.
Okay, grazie, scusate. Now it should be there. So suppose that, let's call E0, 0 and E0 plus. These two quantities be the ground state energy of neutral and ionized atoms. Okay? And one can show that this correction, so by introducing the energy, basically you have to add this quantity to the chemical constant. They must be again, this is a result that at the moment we will not derive, can be justified when introducing the grand canonical ensemble, in which you see that the chemical potential, the role between the interplay, better to say, between the chemical potential and the energy levels of the particles. So once we introduce these two correction, we can compute the chi of electrons, which is the chemical constants of electrons. And in this case, we just need to do, well, the formula was derived already before, it was written already in the previous page. But let me single out the part that contains the temperature, as follows. So this is minus 5 half kBt logarithm of kBt, in which I basically consider the fact that you have a kBt to the power of 5 half in the denominator of the log, and so you will have a minus 5 half kBt log of kBt. Then there is a plus kBt, and here we have the log of h to the power of 3. Here we have g minus, I will tell you in a moment what is g minus, and 2 pi m to the power of 3 half. Now g minus is the electron degeneracy, and we will impose that this number is equal to 2 because we have a spin 1/2, of course, of the electrons. Okay, and m, small m, is the electron mass. Okay. Similarly, we can write the chemical constant for the ionized atoms, and we have in front the same minus 5 half kBt log of kBt plus kBt log of, here we have h cubed, here we have a degeneracy g plus, and then we have a 2 pi m plus to the power of 3 half. This is in the log, plus, as I said before, we have to introduce the ground state energy, which we called E0 plus, where G plus, better to write this down, sorry, otherwise I make mess. So this G plus is the ionized atom degeneracy, whereas M plus is the mass of ions. And we have introduced this E0 plus, which is the ground state energy of this atom, ionized atom. Then finally we have a chi0, which is the same quantity but for neutral atoms, in which the first term is equal to the previous ones. Then we have a log of h cubed. Here we have a g0, I guess. Then we have a 2 pi m plus, and I will comment in a moment this, plus E0, 0. Where here I'm assuming that the mass of H0 is equal to the mass of A plus, which means that we are neglecting the mass, the contribution to the total mass of the mass of the electron, which is rather safe as an assumption, okay? And we have introduced here the degeneracy of neutral atoms and the ground state energy of neutral atoms. Now, what we have to do is to apply the formula of the low mass action. So in particular, we have to compute the sum over nu j chi j. Okay? And when you do that, basically you remember that nu1 is equal to 1, nu2 is equal to 1, nu3 is equal to minus 1. Then concerning this term here, you will have that one of them will survive, only one of them will survive, and we will have minus 5 kBt log of kBt. Then we have, by considering the fact that this adds a plus and this adds a minus, I have a plus E0 plus minus E0, 0. And this quantity here will be called I, where I is the ionization energy. Energy is the difference between the ground state energy of ionized atoms and the ground state energy of neutral atom. And it's called ionization energy for clear reason. Okay. Then we have to deal with this term here, these terms. And so we will have plus T. Then we have a log of, let's write it in the following way. We have H3. Now here I should put G minus, but G minus is equal to 2 for what I said before. And so here I have a factor of 2 pi m to the power of 3 half. And similarly, I will have a term. Okay, let me change page because otherwise I make a mess. Sorry. So let me change page. We are deriving, where we are writing this formula here, nu j chi j, and we say that this is equal to minus 5 half kBt log of kBt. Then I have a plus I, with this I being the ionization energy, plus kBt logarithm of h cubed divided by 2, and then I have a 2 m pi to the power of 3 half. Then I have a h cubed, and here I have a g plus 2 m plus pi to the power of 3 half, and similar quantity but with a minus for the neutral atom. Therefore I will have a G0 and a 2 pi m plus to the power of 3 half divided by h cubed. Now I can of course make some cancellation, this term here, and this term here. Okay, so finally I have that this formula provides the following result: 5 half kBt logarithm of kBt plus the ionization energy plus kBt, and I have log of h cubed divided by 2 pi m to the power of 3 half. And then I have a ratio between the degeneracy G0 divided by 2G plus. Okay. Now, what is A of t? A of t was the exponential of 1 minus kBt sum over j of nu j chi j. Now I just need to introduce that, so to work out this expression, and let's do it. So here we'll have to make the exponential of 1 minus kBt, and then I have to introduce the sum that I just derived, sorry. And here I have a minus 5 half kBt log of kBt plus I plus kBt log of h cubed 2 pi m to the power of 3 half and G0 divided by 2G plus. And that's it. Equal. Now let me see if I've done the calculation correctly. Here a kBt cancels, then there is a plus 5 half, and then I have kBt to the power of 5 half. as a first term, kBt to the power of 5 half, when I do the exponential of the log. Then I have another term, which is the exponential of minus I divided by kBt. That was expected. You have some experience now in this business, so you expect that somehow the ionization energy must be compared with the temperature. The larger the temperature, in principle, the easier the ionization. Okay, and somehow the interplay with between temperature and ionization must be provided by the ratio between the kBt, which is the thermal energy, if you want, and the ionization energy. So that's why we have an exponential here, which was expected indeed. Then we have, let me see, we have an exponential of minus 1 kBt, so I have a minus. And so I will have a 2m pi to the power of 3 half, 2m pi to the power of 3 half. And then I have a h cubed here, and the ratio 2g plus divided by g0. Okay. Now this is A of t, and remember now by the law of mass action that the product C plus C minus divided by C0 is 1 over the pressure, and then we have A of t, and so will be kBt. Well, let's put all the term. So you have a 2g plus divided by g0, 2m pi to the power of 3 half divided by h cubed. Then we have a kBt to the power of 5 half. Then we have the exponential of minus I divided by kBt. And I think that's it. Let me check if this is correct. Okay. Now let's work out a little bit this expression by introducing P times the volume equal to kBt n, where n is the total number of particles. That means sum of ions, neutral atoms, and electrons. So let's consider this mixture of particles as an ideal gas, as in the beginning, and therefore, instead of P, I can write kBtn divided by the volume, and therefore the C plus, C minus, and C0 now is equal to kBt. So instead of P, let's put kBtn, and then I have a volume. Therefore, I will have 2g plus divided by g0. Then I have the ratio between the volume n and the total number of particles. Then we have a 2 pi m to the, and then h squared to the power of 3 half. I will have a kBt now to the power of 3 half. Okay, because I have a kBt in the denominator, and 5 half minus 1 is 3 half. 2j plus g0 v divided by n. Okay, and then I have the exponential suppression, which is a minus I divided by kBt. Okay. Now this is the law of mass action again for the thermal ionization, and which can be modified a little bit in order to obtain what is called the Zaha equation, which is used, for instance, in cosmology. And what we will do is to derive this important equation. But from this already you can see that once you have the concentration of initial particles and final particles, well, or once you have a mixture of atoms, ionized or neutral, and electrons, you can compute this quantity here, and you can compare with this quantity here in order to see in which direction your system will proceed. Actually, what we will do today with this application is to basically derive an equation for the degree of ionization as a function of the temperature. And in particular, let us introduce three numbers that, well, let us actually compute or write the concentration in another form. So suppose that n plus will be the number of ions, and this must coincide with the number of electrons. By charge neutrality, if you want, or by considering the fact that for each ion you produce one electron. Okay? And suppose that Na will be the total number of atoms, which means ionized plus neutral. Okay? Whereas N was the total number of particles, so ions, atoms, and electrons. Now, by introducing this quantity, we can, let me go here, we can compute the concentrations. Let me change page. In particular, C plus is the ratio between n plus and n, and this ratio is equal to n plus divided by Na plus n plus, because n is the total number of particles, which will be the total number of neutral atoms, ionized atoms, and electrons, but the number of electrons is n plus, okay? So therefore, this concentration is actually equal to C minus. Then C0, which is the concentration of neutral atoms, is provided by Na minus n plus divided by Na plus n plus. Okay? Now let's introduce this quantity alpha, which is the ratio between n plus and Na, and this is called degree of ionization, which of course is a ratio between, well, is the fraction, if you want, of ionized atoms with respect to the total number of atoms. Okay. Now we have to compute in the low mass section this C plus C minus divided by C0, which will be the following quantity. So I have an n plus squared divided by Na plus n plus squared. And then I have to divide by C0, which is Na plus n plus divided by Na minus n plus. Now I can remove one of those factors here, and then I have an n plus squared, and here I will have Na squared minus n plus squared. Now let me divide by Na squared. And we get, by using the definition of the degree of ionization alpha, we will get alpha squared divided by 1 minus alpha squared. Okay, so this is the product C plus C minus divided by C0. So it's alpha squared divided by 1 minus alpha squared. And for the law of mass action, we just prove that this is equal to V divided by N. Then I have a 2G plus G0, which is the ratio between the degeneracy. Then we have a 2 pi m kbt divided by h squared to the power of 3 half, and the exponential minus I kbt. Okay? So I think we have almost done. Let me just make the following. This V divided by N can be written as V divided by this NA plus N plus. Okay. And let's divide by NA. So it's 1 divided by NA V 1 plus alpha, where I derive by NA, numerator and denominator. Okay? In this fashion, this term here is equal to V divided by NA 1 plus alpha, 2G plus divided by G0, 2M pi kBT divided by h squared to the power of 3 half, and then I have the exponential minus I divided by kBT. Okay? So now I can remove this coefficient here, and here I will have just 1 alpha, sorry, 1 minus alpha, okay? Because this is 1 minus alpha times 1 plus alpha, and therefore I can remove this 1 plus alpha. So finally, I get that alpha squared 1 minus alpha is equal to, for, let's say, reasons that are so for the sake of simplicity, one is usually used to write this equation in the following way: single out the factor 2 due to the degeneracy of the electrons, and we introduce a function phi, which is a function of t and volume, where this phi function of t and volume is equal to the volume V divided by NA. So this quantity contains just the part related to the atoms. So it's the ratio between the total volume and the number of atoms, the ratio between the degeneracy of G plus and G0, and the temperature part. So 2m pi kBT to the power divided by h squared to the power of 3 half, and the exponential 1 minus I divided by kBT. Okay? So this equation here is called the Zaha equation. And maybe for those of you who are following cosmology or have done cosmology in the past, maybe they have already seen this equation. I don't know if in this form or in another form. And okay, let me make some comments before going on. Of course, now we can derive alpha as a function of phi, because at the end what we want to obtain is the degree of ionization, which is alpha. And let me change page. So you have to do the following: alpha squared is equal to 2 phi times 1 minus alpha, which is 2 phi minus 2 phi alpha. Now you can solve this second order equation and obtain that alpha which is itself a function of temperature and volume, is equal to minus phi, you can just solve this equation, plus the square root of phi squared plus 2 phi. So now you basically answer to the question in the sense that once you have the temperature, the volume, and the Na actually, which is the number of atoms, because remember that phi, I write it here, is the volume between the number of atoms, G plus divided by G0, to kBt divided by h squared to the power of 3 alpha exponential of minus I kBt. So once you have the species of atoms, so you have the degeneracy, the ratio of the degeneracy, the total number of atoms, which we suppose to be a constant. And this is a constant because in any case, even if you have, for each reaction actually that you have, the total number of atoms is conserved in the sense that either you have a neutral atom or you have an ionized atom. Therefore, this is a constant. And this V divided by Na, if you want, is the density of these atoms. Then there is the temperature, and then there is the ionization energy. So those are the quantity, the input quantities that you need to have in order then to compute the degree of ionization. Okay, so once you have this quantity, you can read out the result for alpha. So you know which is the ratio of particles or atoms in this case that are ionized. Okay, so these are very important result, at least in the context of cosmology, for instance, on the context of, for instance, plasma physics in stars. Let me make some comments here. Now you see that this phi is apart from the exponential, so it's an exponential of minus I divided by kBt. Then there is a t to the power of 3 half. And let's introduce a quantity. This quantity, of course, is I-dimensional, because it's well, it's a proportional. Well, is the right hand side of the Sahara equation. The left hand side is clearly a dimensional because it's a degree of ionization. So then phi must be also dimensional, and therefore, if we have done the calculation correctly, we can write phi as the exponential, which is already a dimensional. Then there is a t to the power of 3 half. And there must be another temperature, T0, to the power of 3 half, okay? For dimensional reasons, where T0, and this is a very important quantity here, you will see in a moment why, what is T0 is everything in this prefactor but for the temperature, okay? So T0 is actually V divided by Na, G plus divided by G0, 2 m pi kb divided by h squared to the power of 3 half. This is to the power of 3 half, which is all the prefactor that you have by leaving out just the temperature. So V and A, G plus G0 to m pi. I think that there is a pi here missing, sorry. 2 m pi kb, okay. And of course, in order to have the dimensions correctly, this is to the power of minus 2/3. Okay? In such a way that once you introduce T0 here, once you 3 half, you multiply 3 half times minus 2/3, sorry, you get a -1, and therefore you get the right prefactor. Okay. So we will compute in a moment this quantity here, which is in front of the phi, of the exponential, sorry, and basically this quantity fixes somehow, well, it determines the degree of ionization. So it's not only the ionization energy which is important, of course this was expected, but it is also important the ratio between the real temperature of the system T and this quantity T0, which was derived basically by considering the properties of the chemical species, because you have the density here of atoms, the degeneracy, and here just have the mass of the electron. So this is a constant. Okay. Now let's work out a little bit more this result. So let me start from this. Alpha is equal to minus phi plus phi squared plus 2 phi square root. And we can see, of course, this is the solution to the problem because it provides the degree of ionization as a function of temperature and volume, where phi is equal to 2t divided by t0 to the power of 3/2 and exponential of minus I kBt. And now we can see that this function phi, let's work out the limits in which the temperature is small and the limit in which the temperature is large. For t going to 0, you see that phi is also going to 0 because you have exponential suppression to this, right? And then you have an additional t to the power of 3/2, so it's going to 0. For t going to plus infinity, so large temperature, phi is also going to plus infinity. Okay. And in these two limits, we can derive an analytical formula, well, a simple scaling between alpha and phi. So let me write this fashion. We can determine the scaling of alpha with phi. At least in these two limits, we can derive a simpler formula. Okay, let me take another piece of paper. Okay. So suppose that we have t, which is going to plus infinity. We said that the phi goes to plus infinity. And therefore, in this formula, alpha was minus phi plus phi that I can collect 1 plus 2 divided by phi equal to minus phi 1 minus square root of 1 plus 2 phi. And you can expand this term here, which is will be 1 plus 1 over phi minus 1. Well, you can do the calculation if you want. And you should have here minus 1 divided by 2 phi squared plus other terms. Of course, if phi goes to infinity, this is an infinitesimal quantity, and we can Taylor expand this expression. So this is minus phi, then we have a 1, minus 1, minus 1 over phi, plus 1 divided by 2 phi squared plus other terms. So this goes away. And then I should get that this is almost equal to 1 minus 1 divided by 2 phi. Okay? So this alpha is equal to 1 divided by 2 phi for large temperature. Okay. Of course, phi goes to infinity. Alpha is equal to 1, so total degree, so the degree of ionization is 1, means that everything is ionized, every atom is ionized. And the first correction is this correction, 1 divided by 2 phi. Similarly, for t going to 0, we said that phi is going to 0. And in this case, easily we can say that alpha is dominated by the square root of 2 phi, because this is the leading term in this case. Okay. So those are the two scalings of alpha, the degree of ionization, once we consider the limit of large temperature and small temperature. Now, what I want to do next is to provide at least order of magnitude estimate of T0, because phi, we said that phi is provided by this formula, is the ratio between T and T0, this new, let's say, scale of temperature that we have found, that is different with respect to the scale of temperature determined by the ionization. Of course, this is an important scale, I, which must be compared to the thermal energy, kBT, but we have found another scale, which is T0. And this is also important. It's a new scale that appears in this statistical mechanical calculation. Indeed, actually, when doing calculations in statistical mechanics, very often what is important is to find the prefactor. So one can infer that if you consider a problem of ionization, there must be an exponential suppression in which you have the ratio between ionization energy and the thermal temperature and the thermal energy, but you have also a prefactor which could have an important role. Okay. Indeed, what we want to do now is to provide an estimate of T0. And let's try to do it. So now remember that T0 was this formula here. I think I wrote this before. And yeah. So let me write it in the following way. So it's Na divided by the volume to the power of 2/3. Let me check if this is correct. Yeah, to the power of 2/3. Then I have a G0 divided by G plus, again to the power of 2/3. Let me check if this is correct. Yes. Okay, and then I have a h squared 2m pi kb h squared, and then I have a 2m pi kb. Okay. Now, to do the calculation, let's make the following assumption on those numbers. So let's take Na order of Avogadro number, for clear reasons, because those are the typical numbers in macroscopic systems. Let's take V as 1 meter cubed. So since I like to work in natural units, let me introduce microscopic quantities. So V could be of the order of 10 to the 15 Fermi to the power of 3. Okay. Then we have the speed of light, c, that will be introduced for reasons that will be clear in a moment. And this is 3 10 to the 23 Fermi per second. Then remember that we have an H bar C, which is equal to 200 MeV times Fermi. Then we have the mass of the electron, which is equal to 0.5 MeV. That's why I like to work in natural units, because I remember the mass of particles in MeV. And in natural units, Kb is equal to 1. So the constant, the Boltzmann constant, is equal to 1. Okay? So let me change page. So this formula of T0 is now Na divided by V to the power of 2/3. Then we have G0 divided by G plus to the power of 2/3. Now let me introduce the H and H bar. Is the relation is that H bar is H divided by 2 pi. So I can introduce a H bar squared C squared. Then I have a 2 pi m, the denominator, and then I have a 4 pi squared. Okay, where I'm multiplying by the speed of light in order to get the right dimension. Let me check just a moment. So I have Na divided by volume, G0 and H square, blah, 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 2m pi, 4 pi squared. Okay. Now suppose that this is equal to 1 when considering G0 equal to G plus, so I can remove this term here. Volume to the power of 2/3 is a Fermi cubed, so it is a Fermi squared. Here you have a quantity which is MeV times Fermi, MeV times Fermi squared. Therefore, I remove the Fermi square between the denominator and the numerator, and correctly I obtain an energy. Okay, because the temperature in natural units is energy. So this is MeV Fermi squared. Okay, the mass is dimension MeV, and volume to the power of 3 2/3 is again Fermi squared. Therefore, I remove the Fermi squared and I get MeV squared divided by MeV. So that's correct. It's always useful to do this dimensional analysis. We know that the temperature must be an energy in natural units. And once you introduce the number, if I have done the calculation correctly, you should get something of the order of 10 to the minus 9 MeV. Okay. Now remember that 10 to 10 Kelvin is almost equal to 1 MeV. So in order to make so to change between Kelvin and MeV, therefore this temperature, if I want to express it in terms of Kelvin, is of the order of 10 Kelvin. Okay. So a few degrees in the scale of Kelvin. Okay. Whereas I is of the order of electron volt in atomic physics, if you want. Order of electron volt means, so this is atomic physics scale, of course, means in terms of Kelvin, means, let me see, I have 10 to 4 Kelvin. No, because 1 MeV is 10 to 10, I divide by 6, so, well, I have 6 orders of magnitude, and therefore 10 to 4 Kelvin, 10 to 4 Kelvin is the factor, so the temperature corresponding more or less to the ionization energy, which will be of the order of the electron volt. Okay, so just to make an order of magnitude estimate. Okay, so now you see that the ionization energy, which has a scale of the electron volt, or in terms of kelvins of the order of 10 to the 4 Kelvin, is much larger than T0, which is instead is of the order of 10 Kelvin. Okay, so this is important because now we have two scales in the system. One of them was already somehow intuitive, which is the scale of ionization energy, and we have another scale, which is this T0, coming from the statistical mechanics calculations, which is actually much smaller. Is of the order of 10 Kelvin. Now, the fact that these two scales are different, are so different, is responsible for the fact that even if we are not at the temperature which is close or to very close to the ionization energy, actually we will have a certain degree of ionization in any case. Okay, so also in this room, of course, the temperature here is of the order of 300 Kelvin, is rather, so it's very much suppressed with respect to the ionization energy. Nevertheless, there will be, in any case, a certain degree of ionization due to the fact that the ionization, the degree of ionization, is determined by the exponential suppression, but there is a prefactor, which is T divided by T0 to the power of 3/2. Okay? So if T0 is very small, of course, the ionization, the degree of ionization is large at a fixed value of the temperature. Okay, and indeed, in order to make a let me maybe write this. So if T0 is small, I have a finite, if you want, finite degree of ionization, even if I'm not at the temperature corresponding to I, to the ionization energy. Okay. Indeed, to make this calculation a little bit more sensible, in order to fix the scale, let's put phi equal to 1. In this case, for the formula that we had before, the degree of ionization, if is phi is equal to 1, is of the order of 70%, 0.7 in this case. Okay. Now, what we can do is to determine which is the temperature corresponding to this degree of ionization. So we put phi equal 1, in this case alpha is equal to 0.7, and we can compute which is the temperature, find Tc, the temperature corresponding to phi equal 1, which is also alpha equal to 0.7. Okay, and let's try to do it. So now phi is equal to T divided by T0, but let's put Tc here in order to find, well, okay, let's do in the following way. Let me change page first of all. I'm almost done, then I will make a break. Just a moment, almost done. So remember that phi was the ratio between t and t0 to the power of 3 alpha and e to the minus I kbt. Now let's put phi equal 1, and let's call the temperature for which T is equal to 1, let's call it Tc, now critical temperature if you want. Tc is a sort of critical temperature. For having alpha equal to 0.7. Okay. So let's see what to do. Here you have that the exponential of I divided by kbTc is equal to Tc divided by T0 to the power of 3 half, where I'm using this equation. Let's make the log of this. So I divided by kbTc equal to 3 half log of Tc divided by T0, and I divided by kbTc is equal to 3 half. Let's make the following trick. Let's introduce I log of I divided by T0 minus 3 alpha, the log of I divided by Tc. Let me check if this is correct. I have just introduced a factor of I in the numerator and the denominator of this. So therefore I will have I divided by T0, then I have plus Tc divided by I, but then so I can add the factor of minus, and then I have the ratio between I and Tc. So this should be correct. This should be correct. The log of Tc divided by T0. Okay. Okay, so now what I will do, now the aim of this calculation is to find an expression of Tc, and that's why I'm making this trick. So to neglect this term here, neglect, because I expect that I divided by T0 is much larger than I divided by Tc. Or if you want, I expect Tc to be much larger, or in any case larger than T0, because T0 is the scale, the smallest scale in this calculation is 10 degrees in Kelvin. Okay. So if I neglect this term here, basically I can get a final correction, a final result for Tc. So if you neglect this, then you get that Tc is equal to I divided by Kb divided by 3 half the logarithm of I divided by T0. Okay? So this is the critical temperature for having phi equal 1, which was also alpha, degree of ionization equal to 70%. Okay? And you see that in order to get the 70% degree of ionization, well, actually, I get a suppression factor here. So here I have the ionization energy, of course, which is important. which is in any case suppressed by a 3/2 log of I divided by T0. Now, in this specific example, I and T0 were of the order of 10 to 4 divided by 10, so it's a factor of in the log I have a factor 10 to the power of 3, and therefore I have a suppression here which is 3/2 log of 10 to the power of 3. Okay, so then I can put the 3 outside, I get a 9/2 times the log, natural log of 10. Okay, so this provides somehow, so tells me, is telling me that TC is smaller than I. Okay, of course, so TC smaller than I by a factor 3/2 log of I divided by T0. Okay, so again, this result, so this, well, it's another way to see that actually to have a certain degree of ionization, in this case 70%, I do not need to sit at the close to the ionization energy, because the prefactor that we derived actually is making a strong contribution. Okay, so maybe before the break, I just want to comment on another fact, and then I will stop. I promise. Now we said at some point once we have degeneracy, we have to correct the chemical constant with a factor 1/g in the log, and I want to justify this. When computing the entropy in the microcanonical ensemble, we said that S was provided by Kb, and here we had the log of V to the power of n, which was the volume to the power of n, plus other terms, okay, in the microcanonical ensemble. If you remember, the microcanonical ensemble, the calculation was actually to compute the volume of a layer in the hypersphere of the phase space. Okay, well, actually at some point we said actually this layer has the volume of the sphere, so then basically what we have to compute is to compute the volume of this sphere in the phase space, but this volume gets a term which is v to the power of n from the integral over momenta, over coordinates, sorry, and then we have another term which is related to the integration of the momenta. But of course we have a log of v to the power of n, okay? Now once you have degeneracy, each of these integral over the coordinates gets a degeneracy factor, okay? So this was coming from the integration over dq, dq3n if you want, okay? Each of these integral gets, once you have degeneracy, g to the power of n. Okay? Therefore, in the expression of the entropy, we will have an additional kb, log of g to the power of n plus other terms, which means also that we have that the entropy will be nkb log of g plus all the other terms, okay? Since the degeneracy will just multiply the volume, okay? So if I have the volume to the power of n, I will have also degeneracy to the power of n. That's basically the thing. Now, to compute the chemical potential, at some point we have to do this. Minus T derivative of S with respect to N at fixed U and fixed volume. This is what we have done. And therefore, I will have here an additional, since I derive with respect to N and I have a minus, I will have an additional minus KBT log of G. Okay? To be added to chi of T. And the mu was written in terms of a sum over chi of T, which is the chemical constant. Mu was equal to kBT log of pressure plus chi of T. Okay? And so if we have degeneracy, we have an additional minus kBT log of G that needs to be added to the chemical constant. And therefore, the chemical constant will be chi of T will be the previous one. So kBT log of lambda cubed divided by kBT minus kBT log of G. Okay, which of course then becomes, that means that you have a kBT log of lambda cubed divided by G kBT. And therefore this degeneracy goes into the denominator of the logarithm in the chemical constant. Okay, like this is a way to do it, but there is another way, and we will do it next time. Well, when we will deal with the grand canonical ensemble. Now it's 10:30, so I think it's good for us to make a break, at least 5 minutes. And I'm sorry for that, but I wanted to finish this part. And so let's stop for a while. I continue?
Yes, Prof.
Posso riprendere?
Sì, sì, Prof. Beh, non va. Sì, Prof.
Ah, sì, non si sente molto. Come mai? Vabbè, comunque riprendo. Okay, now we change topic. This last calculation was the final part of, let's say, microcanonical ensemble. Now what we'll do is to move to the canonical ensemble, classical canonical ensemble. Canonical ensemble. So I'll remind you first what was the microcanonical ensemble. The microcanonical ensemble was an ensemble in which you have the energy is fixed, the volume is fixed, and the number of particles, they are all fixed. And this is, let's say, the situation in which the system under study is isolated. Okay, so there's no exchange of energy or work or heat or particles between the system and the environment, if you want. And in the case, in this situation of the microcanonical ensemble, you take your Hamiltonian, it could contain kinetic terms or also terms having the interaction. And what you have to do is to compute the volume in the phase space occupied by your system once you have the constraint the energy is fixed, or better to say that the energy is between, let's say, the Hamiltonian is between E plus, is between E minus d delta divided by 2 and E plus delta divided by 2. So a small layer corresponding to an uncertainty in the energy. So then in the microcanonical ensemble, the calculation is basically to provide the calculation of a volume in the phase space, which is compatible with your constraints on volume, energy, particular energy, and number of particles. This calculation is usually very complicated. Actually, it's easy, but somehow not straightforward for the case of kinetic, just Hamiltonian with kinetic terms, but it gets very, very complicated once you introduce interactions. So it gets almost impossible to compute such a volume, okay? In the case in which you have also interaction between particles. And the fact that you computed the volume occupied by the phase space in the phase space by your system corresponds to the assumption that all the microstates have the same probability to occur once they are compatible with the constraints of total energy E, volume V, and to the number of particles N. Okay? So these were the assumption, the way the microcanonical ensemble was derived. Now, the canonical ensemble is actually more useful when dealing with systems in which interaction is present, because as I said before, computing that volume in presence of interaction becomes very complicated, and it is much better to work in the canonical ensemble. What is the canonical ensemble? Basically, the idea is the following, is to consider a system which I call T, say the total system, And in this system, we basically single out two other systems, a small one that I call S, and another, the complementary R, which is a reservoir. So S is the system to which we are interested. Okay, T is the total system, and R is a reservoir of energy. So a system with heat capacity going to infinity. And basically the role of the reservoir is to fix the temperature of the system S. Okay? The role of the reservoir is to provide energy to S, well, to provide or to extract energy, okay? Extract. Yes, in such a way that S has a fixed temperature. So differently from the case of the microcanonical ensemble, now the system to which we are interested is not isolated, but it can it can exchange energy with a reservoir. And the reservoir has a large heat capacity, infinite heat capacity, which means a large system. For instance, it could be the sea. And the small system S instead is exchanging energy. So this time its energy is not fixed, differently from the case of the microcanonical ensemble. Okay. Now let me change page. The total system. So we treat the total system T in the microcanonical. Because the total system is isolated, whereas its two parts, S and R, are not isolated and can exchange energy among themselves. Okay? So if the total system is in the microcanonical ensemble, we treat in the microcanonical ensemble, we can say that the rho of T, so its distribution function or its ensemble, is constant, where if H of T, the Hamiltonian, total Hamiltonian, is smaller than Et plus delta alpha, as before, as in the microcanonical ensemble, is exactly the same. Whereas rho of T is equal to 0 elsewhere. Okay, so it is exactly the microcanonical ensemble applied to the total system. Okay, and if you remember, to compute the microcanonical ensemble, we have to determine, apart from some normalization factor, which can be fixed at the end, V omega of T, which was the total volume occupying in the phase space, which was this integral over dq and dp, with the constraints that the Hamiltonian is smaller than Et plus delta divided by 2, larger than Et minus delta divided by 2. So these are all the microcanonical ensemble for the total system, so the same equation. Now let us introduce the fact that the total energy is equal to the energy of the system S plus the energy of the reservoir, first of all. Okay. And let's also specify the fact that dq dp is actually dqs dps dqr dpr, where the first two coordinates and momenta refer to the system S, and the R and the dqr dpr refer to the system R, which is the reservoir. Okay. Therefore, the d, if you want, d omega t is equal to d to the product dqs dps and dqr dpr, if you want. Okay, so the infinitesimal volume occupied by the microcanonical ensemble of the total system is just a product of these two infinitesimal volumes. Okay, we can also indicate this as d omega s times d omega r. Now the difference between the canonical and the microcanonical ensemble, that now we ask ourselves the following question: which is the probability apart from normalization that the system small s is in a certain state, well, microstate. This is important regardless of the state occupied by the reservoir. Okay, so basically what we do is to neglect, well, actually to integrate, and let me write this, we integrate over the reservoir possible microstates. Okay, and therefore we will write, if you want, this was so let's start with this. D omega t we said is equal to d omega s and d omega r equal to d qs dps dqr dpr. We basically integrate over dqr and dpr, okay, and we get what we can call a d, let me see how to write this part here. Let me see how to call it. When I integrate over this, I get, when integrating, will provide omega r, okay, which is a volume occupied in the phase space, but for what concern the reservoir. And therefore, I have d omega s, this point. If you want, this is let me see how I can call it in a better way. I, where this I means I have integrated over all the possible states of R, which will be equal to a certain normalization constant times the volume omega r on which I'm integrating over dqs dps. Okay. So basically, I've taken the previous expression, I am integrating over all the possible states of the reservoir, and I get a volume in the phase space, which is omega r times a certain normalization factor A that will be determined at the end of this calculation. Okay, and this is an infinitesimal volume occupied in the phase space, but for the system small s. Okay. Now, in the microcanonical, now the difference with respect to the previous case is that in the microcanonical, when I was writing d omega is equal to dp dq times a rho, this rho was constant. Whereas in this case, this is not the case. Okay, now this function here, it's a density, it's a distribution function rho, which is not constant in this case. And let's see how to determine this distribution function that at the end will be really just the canonical ensemble in this case. Now remember that S of R, the entropy, is Kb apart from normalization, the logarithm of omega R, because here this equation is true if I consider the relation between entropy and the volume of the phase space within the microcanonical context. Okay. Microcanonical ensemble picture for system R. Okay, because basically the reservoir and the total system are basically the same system. Okay, so the total entropy I can use as the same formula that I was using in the microcanonical ensemble to the total system, but also to for the reservoir, since the reservoir is basically just the total system, because the system S is very small, and the reservoir has an infinite heat capacity. Okay. So from the previous equation, the exponential of S of R divided by Kb is equal to omega R. Okay. Now let's write SR, which is the entropy of the reservoir, as a function of ER. This will be in general. Now this SR will be a function of ER, but ER, what is ER? Is related to the total energy ET and the energy of the system S in the following way. This S of R is a function of ET minus ES. Okay. Now consider this as a Taylor expansion. In which the perturbation is the ES, which is the small quantity in this calculation. So therefore, this is almost equal to the S of R computed at the energy ET, which is the energy of the total system, minus the partial derivative of S of R with respect to ET times ES. Okay. Um, well, actually, with respect to its argument, so this will be actually ER, okay, times the perturbation. Okay. But now, so the SR of ER is equal to SR computed at the energy ET minus ES times the derivative of S with respect to ET or with respect to ER is 1 divided by KBT. The derivative of S of R with respect to ER is equal to 1 divided by KBT. Because this is the relation between the temperature, the entropy, and the total energy in thermodynamics. Therefore, I get this useful relation between S of R of AT and ES and temperature. So now this d omega Si that I wrote before, it was A, this normalization factor, omega of R, dqs, dps. Now this is equal to A times, instead of omega R, now I can compute, so I have the exponential of the entropy, no? So you have the exponential of SR computed ET divided by KB times the exponential of minus ES divided by KBT. Okay. Let me check if the calculations are correct or if I'm forgetting something. Maybe there is a mistake here. Yes, here there should not be a KB. Sorry, there's no KB there. Okay. Derivative of entropy with respect to energy is 1 over what? Sorry, yeah. Let me write it back again. It's 1 divided by the temperature. Yes, because TdS is equal to dU times PdV. Okay. And then I have a KB at the denominator there. Because this was, and of course this is not present anymore. It's just T. Yeah, okay, that should be correct now. Then I divide by KB, and so now KB minus KBT. Okay, good. Then I have the dqs here and dps. Okay. Now let me introduce this quantity here, and let's call it C. And this quantity here, I leave it like it is. So d omega Si integrated over the states of the reservoir now can be written as rho times dqs dps, where rho is equal to e to the minus es divided by kBt times this normalization constant c. Okay. And how we normalize this rho? We normalize rho in such a way, let me change page. Here. we normalize rho in such a way that the integral of d omega s integrated is equal to 1.
Scusi il foglio, prof.
For reasons that will be clear, I have not changed page, sorry. So let's impose that this is equal to 1, and therefore the constant c will be equal to the integral of e to the power of minus es kbt dqs dps. Therefore, at the end, rho is equal to e to the minus es divided by kbt divided by the integral of e to the minus es kbt dqs dps. Now, this formula here is the canonical ensemble. It's called canonical ensemble. Canonical ensemble. Okay. And now it's 11, we will discuss later, which is the interpretation of this ensemble and how to use it in practice. Okay. Okay, see you next Thursday.
Arrivederci.